All right, hi everyone. Okay, so I'm going to talk about a project I did with these folks. You can find the paper here. So I'm going to tell the story sort of chronologically here. The original question that we wanted to answer is what sets the intrinsic scatter in the star-forming main sequence. So I should tell you what the star-forming main sequence is. It's this, I'm sure you all know, the correlation between stellar mass and star formation rate in star-forming galaxies. It exists across a variety of redshifts, and it has some finite scatter, so about a factor of 2. So the question we want to answer is why do galaxies at a fixed mass have a variety of star formation rates? So one obvious culprit here is the fact that dark matter halos are known to have a substantial scatter in their accretion rate. So if you look at the difference in mass of a dark matter halo at 2 different times, you find that in a dark matter only simulation that you get a log normal distribution in your accretion rates. So that's a good candidate for producing scatter in your star formation rate. But something else which is important is the timescales involved. So what do I mean by that? If I tell you that my accretion rate has this scatter in it, but then I tell you that this timescale is a week, the galaxy doesn't care about all this scatter because it's happening too rapidly for the galaxy to do anything about it. But if it's a gigayear, then the galaxy cares. So to incorporate both of these effects, we produced a very simple model. This is a standard bathtub model. So here's my galaxy. It has a gas mass, and we feed it with a log normal accretion rate, and the galaxy produces stars and winds at some rate proportional to its current gas mass. So it's a very simple model. This accretion rate we separate out into a slowly varying median accretion and a potentially rapidly varying log normal component. And the way this works is at fixed time intervals, we draw a new value of the accretion rate. So the accretion rate will look something like this in log space. So we can derive a solution to this equation analytically, and it depends only on 2 dimensionless numbers, sigma and the ratio of those 2 timescales I've defined. And here's how the galaxy behaves. So on the y-axis, I'm showing you the star formation rate, and on the x-axis, I'm showing you time. And these dashed lines are where are new values of the accretion rate as they're drawn. And you can see that the galaxy just sort of monotonically approaches new values of the accretion rate every time a new one is drawn. And you can imagine if I increase sigma, the galaxy will have a larger spread in star formation rates. But if I change the timescale, if I make the coherence time much shorter compared to the mass loss time, then the galaxy doesn't have time to get to the new accretion rate and is sort of stuck jittering in the middle. So now what we can do is we can systematically explore this parameter space by simulating a bunch of different galaxies at the same time. And we can map out the whole parameter space. So here I'm showing you the intrinsic scatter that we put in and the ratio of these 2 timescales. And each pixel here is an ensemble of 10,000 galaxies for which we're measuring the resulting scatter in the star formation rate. And you can see that as you increase the intrinsic scatter and as you increase this ratio of timescales, you get a larger scatter in the star formation rate. And you can compare this to the currently observed scatter in the star formation rate, and that immediately rules out a big part of this parameter space. You see that you need to be sort of in the lower left here. We can also add metallicity to this model. And the point here, so on the top I'm showing you star formation rate, and on the bottom I'm showing you metallicity for the same galaxy. And the point I want to get across here is that they behave differently. So the star formation rate monotonically approaches new values when a new accretion rate is drawn. But the metallicity always tends, even though it has deviations, it will always tend back to this equilibrium value. So they behave very differently, so they give you complementary constraints. And not only can we measure the scatter in the metallicity here, you can also measure the correlation. So that gives you 3 sort of independent constraints. So you have So this is the scatter and the star formation rate, this is the scatter and the mass metallicity relation, and this is the slope, i.e. the anti-correlation between the star formation rate and the metallicity at a fixed mass. And you can overplot the sort of standard, the observed values of these scatters, and I should point out again that these are upper limits. So the observed scatters can have observational error in them. So the observed scatters are sort of, you can think of them as an upper limit on the intrinsic scatters. So these lines give you upper limits, so that constrains you to be in this part of the parameter space. And then the slope in the fundamental metallicity relation forces you to be sort of between these two lines, although there's a lot of systematic uncertainty there. So you can immediately see that you tend to be forced to a relatively small part of this parameter space. So this is all nice. This is a simple non-dimensional model where I have where I'm showing you what happens when I vary the input scattering the accretion rate and this coherence time. But what do we expect to happen for the real universe? And for that, we redimensionalize these parameters. So the parameters that go in here are so this ratio of the coherence time, this tau coherence is the ratio of the coherence time to the mass loss time. Mass loss time includes the mass loading factor, which is very uncertain. It includes the depletion time, which is also very uncertain as both a function of mass and redshift. So we basically put in scalings for these that would reproduce the redshift 0 star forming main sequence, the mass metallicity relation, and the relationship between gas fraction and stellar mass. And then what we did is we can now systematically vary sigma and the timescales and produce synthetic versions of these relations and then compare them to the observed scatters. So here are the constraints we get as a result. So here what I'm showing you is the scatter that the dark matter scatter that we put in. And up here is the coherence time. So this little square is like the plots I was showing you before. And then here's some additional sources of scatter that we put in. And basically the way this works is at every pixel here, we check does the model produce a scatter that's too large in one of these relations or a slope that's too steep in one of these relations. And every time it violates one of these constraints, it gets a shade redder. So the white cross here is the initial guess we had based on the dark matter simulations. So we put in a scatter of 0.45 dex, which we got from basically the formula I showed earlier. And you can see that in this model produces too large a scatter in the star-forming main sequence. The other really striking thing is that the scatter in the mass loading factor is forced to be small. So we find that so you can imagine, you're trying to explain the scatter in the star-forming main sequence. One way you could imagine doing that is changing the mass loading factor. But it turns out that we find that you can't do that. And the reason is basically that in equilibrium, the metallicity and the star formation rate both depend on the mass loading factor eta in the same way. So if you put a large scatter in the mass loading factor, you push the metallicity and the star formation rate in the same direction, and that creates a correlation. Whereas in the real universe, there seems to be an anti-correlation between the star formation rate and the metallicity. So, okay. So one final important issue is where might you expect this model to be valid? Where is it reasonable to treat these galaxies as having lived in that distribution I showed you forever? And so what I'm showing you here is the time it takes for the galaxy to reach, the population of galaxies to reach statistical equilibrium compared to the Hubble time. So blue means that the galaxies equilibrate quickly relative to the Hubble time. Red means they don't. And basically, this all depends on what you put in for the mass loading factor. If you put in a steep mass loading factor that scales as halo mass to the minus 2/3, which is what we did in our fiducial set of models, then this seems like a reasonable model pretty much everywhere in halo mass and redshift space. But if you have a weak feedback scenario, then this loss time that we put into our model doesn't vary strong. Like T depletion is varying too strongly, and eta isn't compensating. So the mass loss time becomes very long in these low mass galaxies, and they never reach equilibrium. So, and I'd say that the observations can't necessarily distinguish between these two scenarios right now. So really understanding the mass loading factor is particularly important for distinguishing whether galaxies are in equilibrium at low mass. Okay, so my summary is including a realistic scatter in the accretion rate can produce a substantial scatter in the star-forming main sequence and these other scaling relations, and maybe even too much. The scatter in mass loading factor at fixed mass has to be small to avoid a not observed correlation between the star formation rate and the metallicity. The scatter in the accretion rate of baryons may be smaller than that of the dark matter. So it seems like the intrinsic scatter that the galaxy is seeing needs to be smaller than what we would expect from dark matter. And measuring and predicting the mass loading factor is fundamental for understanding the nature of these galaxies, especially dwarfs.
Thank you. So Simon, if you want to come up, and Simon, come up with the first question.
Would you agree, like, I find this very interesting, would you agree that your starting point, if you like, is constant accretion rate, whereas my starting point has been constant specific accretion rate, and that some of the differences in the conclusions come from that difference, and would you agree with me that reality probably lies somewhere in between?
I think that's probably fair.
Yeah. In my analysis,
yes.
If you fix the gas mass, okay, which I think is what effectively is happening here,
Yeah.
then again you always tend to the same metallicity and so on. So I completely agree with that.
Right.
But I suspect, as I say, reality lies between the two sort of.
Right, because you're following galaxies through their cosmological history, whereas I'm sort of approximating them as having lived in the same distribution forever. Yeah, I think that's fair.
Any other questions at all? Okay, in that case, it just remains to thank John again.
In star-forming galaxies, it exists across a variety of redshifts, and it has some finite scatter, so about a factor of 2. So the question we want to answer is, why do galaxies at a fixed mass have a variety of star formation rates? So one obvious culprit here is near star formation rate. But something else which is important is the timescales involved. So what do I mean by that? If I tell you that my accretion rate has this scatter in it, but then I tell you that this timescale is a week, the galaxy doesn't care about all this scatter. All right, hi everyone. Okay, so I'm going to talk about a project I did with these folks. You can find the paper here. So I'm going to tell the fact that dark matter halos are known to have a substantial scatter in their accretion rate. So if you look at the difference in mass of a dark matter halo at 2 different times, you find that in a dark matter only simulation, that you get a log normal distribution in your accretion rates. So that's a good candidate for producing scatter. I'll tell the story sort of chronologically here. The original question that we wanted to answer is what sets the intrinsic scatter in the star-forming main sequence? So I should tell you what the star-forming main sequence is. It's this, I'm sure you all know, the correlation between stellar mass and star formation rate